All right, so the second part of chapter 10 is what I'm going to talk about. That actually has to deal with sorting and searching. If you can read the slides or the book, but they essentially explain a couple of different types of searches and there's a couple of different types of sorting. So I'm going to go ahead and start off with the sorting. So the first sorting or sort that they talk about is what they call the selection sort. So the way this works is if you have a list of items or a list of data, like an array of data, you're going to implement two loops in order to do your search. So just say we have an array and we have some values inside of this array, like 7, 9, 13, 15, 17, 1, 0. It keeps going. Okay. So the first loop is going to look at every element. Like it's just a loop that's going to just look at every element. It's going to keep going all the way up to the end. And it's actually not going to look at the very last element in the list. But then the second loop for each iteration is going to compare itself to what's left in the list. So for instance, the first item is 7. It's going to say, okay, well, my min value is 7. The 7 is 9 less than 7, is 17 less than 7. It's going to keep going. Or that's actually 13. This first one right here is 13. It's going to keep checking everything in the list. And when it finds something less than it, it's going to update this value here instead of like the value that is less than the item here. And once it's done, it's going to do what we call a swap. So like 0 is obviously the smallest value. So it's going to like once the inner loop is done searching, it's going to swap those values. So then the new updated array would be 0 would be in front. Then you would have a 9, then a 13, a 15, 17, 1, and then your 7 would be right there. Right, your 7 would be right there, and then you keep having the rest of the items. And then it's going to look at the 9 and do the exact same thing. So it's actually a pretty simple sort. So this is what we call the selection sort. All right, so let me go ahead and just implement that really quick. I did create a project already, and it's called what did I name it? It's called sorting example. And I've done this example a few times, but I keep messing up because I'm not using the right mic or there's like weird background noises and all that. So hopefully this is the last time I have to make this video. Or yeah, so let's begin. All right, so what I'm gonna do is I'm gonna do the thing where I normally do, where I just have like different methods that I call. So I'm gonna have a public static void. I'm gonna call this one test float array sort. Okay, so what I'm gonna do inside of here is I'm gonna make an array that holds floating point values. And I'm going to just put some values inside of here. And we'll just like 4.5, 7.8, 1.2, 3.4, 0.1, 2.7. All right. And it is a float, so I need to come and put the F on it so that it's a float literal to Java. And then what I'm going to do is do the for each loop where I pull out the value from my array and just print it out. All right, so I'll print out num. All right, so what I'm going to do is do this. All right, so I am going to run this really quick so you could just see the list unsorted. Actually, that's not going to do anything because I forgot to invoke this method in my main method. So let me go ahead and rerun this. All right, you can see that that's the way the values are in the array and just exactly the way I put them in. It's unsorted. So I'm going to make this method that's going to do this selection sort for me. So I'm going to call it public static void selection sort, and it's going to take in an array of floats. All right, so this is really simple. I'll try to do my best to explain it as I'm going through it. So you're going to need an outer loop. The outer loop is going to start at 0, and it's going to go all the way up into the entire length minus 1. Wait, I take that back. Length minus 1. Yeah. So normally we go to, while x is less than the length of the array, right? But we're going to take off 1 because we're not going to go to the very last one. We're going to go to the second to the last one. Because once you get to the very last one, you're not actually going to, like, we never want to get to this point, because in the inner loop, we're going to compare to what's next, and there's nothing next. So there's no need to go to the very last item in the list on our outer loop. So that's why we're not going to actually go to the last item in our outer loop. So every time we iterate, we're going to increment. Okay, so now what I'm going to do is I'm basically going to save off that value. I'm going to call it the min value, even though it's technically not the min, but it's the first value I'm starting with. So I'm going to save it off into a variable called min. And I'm also going to save off the index. All right, so now what I'm going to do is I'm starting at this first location and I'm iterating until the end of the array. I'm going to now start from where I'm at plus 1 and then iterate that way the rest of the array and compare and find which one is the min and then do the swap. So I'm going to say int y is equal to x plus 1. Right, so we have the x plus 1 because we're going to start on the very next index, and then you're going to say, well, y is less than values dot length y plus plus, and then you're just going to do a quick check to see if y is less than x. So we're going to say if values at y is less than the min value, that means we have a new min value, and that's going to be values at y. And we have a new min index, which is going to be y. All right, and then once we're done with our inner loop, then we're going to check to see if we did find a min value. So we're basically going to say, okay, well, is min index not equal to x, meaning that the index of where we set our min was didn't change. That means if the very first one that we looked, we set as min, and we didn't find anything smaller, then there's no need to do what we're about to do, which is swap the values. So the way that we're going to swap is I essentially want to take values at x and replace it with the value at min, except I'm going to overwrite what's there and I'm going to lose that value. So I need to like save that value off into a temp value or a temp variable. I'm going to make a variable called temp, and I'm going to save off the value at x. And then I'm going to write min into values x. And then I'm going to write temp to the index of where we found our min. Okay, so that's basically what the swap is we're just replacing that value there. And I named it float up here, the data type float. I'm sorry about that. That should have been int. But yeah, so that corrects that problem. And yeah, so we're basically just swapping. All right, so that should actually do it. I mean, that's it. So I'm going to come over here. I'm going to copy what I did here. I'm going to paste it. I'm going to change this to sorted and make a couple of lines. And then what I'm going to do is do my selection sort and then pass in my number array. And that should sort it for us. Let's see if this actually works. I'm going to run it. And there you go. It just went through that list and it sorted it for us. So that is the selection sort. The next one to talk about is the insertion sort. All right, so insertion sort works just like selection sort, where you're going to have some items inside of an array. Okay. The difference is you're going to start at the second index, and then you're going to go down the list like you were. That's what your outer loop is doing. You go all the way to the end. But every time you examine an element, you're actually going to compare yourself to what's in front. Right? So that's what you're basically, it's the same idea, except you're comparing yourself to what's in front, and you're overwriting the values inside of the loop. And then at the very end, instead of doing a swap, you're just saying, it's going to do like a quick replace, like at the end of the inner loop. And it works the same. The speed is the same, but the book introduces both of them. So what I'm going to do is just copy what I did for selection sort and just modify it to be an insertion sort. So instead of labeling this selection sort, it's going to be insertion sort. And we're going to start at 1. We're going to go all the way to the end of our array. And our min value is going to be the values at x. And our min index is going to be at x. Well, that's going to stay the same. But this is where it gets a little different, is that we're going to actually iterate down. So this is going to be x minus 1. And while y is greater than 0, we're going to subtract. Okay, so basically what we're going to do is if values at y is, this is a little different. We got to swap these two values. So we're going to say if the current min value is less than what we have at y, that means whatever's at min needs to go where y is, and y needs to go wherever min is at. So we're essentially going to just say, okay, well, values at min is now going to equal, I'm sorry, I messed that up. Values at min index is now going to be equal to values at y. So we're basically like overwriting it immediately, and we're changing our index. And we're not going to change min. Min is going to be like whatever value that we first look at all the time. So we're basically just comparing ourselves to what's in front. Then instead of doing this swap here, right, really all we got to do is just say value at min index is going to be min. Okay, let's look at this really quick. I believe that's all we have to do. Okay, so what's happening here is if we're basically looking in front of us, we're saying, okay, we're less than the one person in front of us. The person in front of us is going to take our spot. Okay, we're immediately overwriting it, but we're remembering what index that we moved into our spot. We're retaining this value. This value is not actually changing anywhere. So it's going to retain whatever value we had when we first started this loop, this outer loop. And then if the min index changed, then we're just going to like slide it into its spot or put it to where it needs to be. So that means that if I were to change this from using a selection sort to an insertion sort, I should see the same results. If I did everything correctly, cross your fingers. And yes, seems to be working just the same. Yeah, or did it? Wait, hold on. No, wait. Okay, it did not work just the same. Okay, so I messed something up, probably something minor. Let me just take a quick look, really quick. All right, so the problem that I had with my selection sort, I just was like messing around with it, trying to figure it out. We want y to be 0 at some point, right? So I put y is greater than 0, should be y is greater or equal to 0. And that's where my problem was at. That's why this first one didn't get sorted. So let me go ahead and run this one more time. And now you'll see that you have your unsorted and then our sorted. And it works just the same as it did with the selection sort. So that's the difference between the two, is insertion sort will compare what's in front. Selection sort just would just go down the entire list, find the smallest value, and then do that swap. All right, so the other thing I wanted to show you was sorting objects. So I do have a dog class and a student class inside of this project. They both implement the comparable interface, but they use different things to compare. Like the dog will compare names, while the student will compare test average in order to sort. So but I was going to show you like a polymorphic way of doing this. So I'm going to go ahead and make a method for the dog. So public static void test dog list. Okay, so what I'm going to do is I'm going to make a list of comparable objects. and I'm going to add dog objects into this list. So the dog needs a name, it needs a breed, and an age. Shoot. All right, so I'm gonna make a few of them. I'm just gonna just type in random letters. All right, so what I'm gonna do now is I'm gonna go and just copy what I did. So the algorithm for selection sort and insertion sort, I mean, it's all the same. So the only thing different is what I've done before. I was just sorting items in an array that were specifically a float. So this time what I'm gonna do is I'm gonna take a list of comparable objects and I'm gonna sort them. Okay, now this is where we gotta be careful because the list is a different object. So things like list.length, like if I'm going to go to replace values with list, won't exist because the list actually doesn't have a length. It has a size, right? But everything else is the same. Just kind of come in here and kind of just dress things up a little bit. So this next part, right, where I'm saving off the value of float, like we don't have floats in this list. They're comparable, so I'm going to say comparable. And instead of doing list and then the, instead of doing list and then the index, what I'm going to do is, or actually what you have to do is do like get and then the index that you want to get. So in this case, I want to get list, get X, and I'm going to store that into min, the variable min. Here, we're going to do the same thing that we did up here. Instead of using values length or length, we're going to use the list size. Then here, whenever we're going to get a value, we're going to get the list. We're going to get it. Or we're going to say Y. Okay, now we can't use the comparison operator because those are for primitive data. So what we actually have to do is do the compare to. So we're going to compare to min. And if it's less than 0, that means it's less than. Okay, and then we're going to say min. Here, we'll say list.get Y. So we're just basically just restructuring this, or the algorithm's the same, but we're just changing the code to handle a list of comparables. Down here where I'm setting up where I'm doing my swap, same thing. It's gonna be comparable temp, but I'm gonna go ahead and get X. All right, and we're doing our set. This is going to be a little different. List, actually, let me just Control Z this. I'll write the line underneath it so you can see the comparison of how it looks. So I'm going to say list.set and then X, and I want to pass in min. Okay, so we can get rid of this line. And this line is the same thing as saying list.set min index temp. All right, and that should do it. That should sort our list of comparables that has dogs. But what I'm going to do is I'm going to kind of do what we did for this float of array, where I print out the list unsorted and then sorted. Say unsorted, and we have a list. Call it com for comparable. All right, and this is comparable. All right, I'll just copy what I did here and then pass my list of comparable objects to my selection sort. All right, yeah, that should work. So let me just change or call this method from the main method and run this program. All right, so if you look up at top, the unsorted, it's exactly how I typed it in. And then we have the sorted, which is went off the name. We could do, since it's taking in a list of comparables, I can just copy what I did here, paste it, and change, like make a method for the student. Okay, and this change, let's see, what am I going to change? All of this stuff. All right, so the student constructor takes in first, last name, and then 3 test grades. So we'll just say this one was 100, 98, 87. I'm just going to just type some values in here. All right, so we go ahead and run this. Actually, I need to invoke this method. So really all I had to do is just change the data that I had in that list. So now when I run this, you can see the unsorted students is like so, but then when they're sorted, it sorted them by test average, and that's the way they came out sorted. So that is insertion and, excuse me, yeah, that's selection and insertion sort. So pretty straightforward. Well, I mean, once you have the algorithm down, it's the same thing. Just you gotta manipulate whatever data structure that you're using in order to put things in the correct order. Okay, so the book also covers searching, which is pretty interesting. It introduces you to 2 types of searching. So you can read these slides and all that. It's actually pretty good. A lot of good information. But I'm going to go ahead and just draw this up. So the first type of search that the book talks about is what they call the linear search. All right, this one's pretty obvious. I mean, essentially you have like some needle. We'll say like, we'll call this needle. Like, right, does that look like needle? All right, and it's like, say we're looking for 7. Okay, you're gonna start at the very beginning and then just look at every item in the list until you find 7. And once you get to the end, you don't find it. Okay, you just start from the very beginning, and that's the way you search. The next one, or the other thing it talks about, is called the binary search. This one's actually a lot more interesting. You have a list of items. Okay, but in order for the binary search to work, this has to be sorted. Okay, and this, like, say you're looking for a needle called, I don't know, just say, well, it's not called, but just say you're looking for the value like 18. Okay, no matter what value your needle is, you're always going to start in the middle. Okay, and then you're going to check whatever value is here and say, okay, well, am I greater than or less than? If you're less than, then you're going to search this portion of the array. And then you're going to search the middle of that. If it's less than this, whatever value is here, you're going to search this portion of the array, right? Over here, if you're greater than, you would search this portion. And so basically, you're going to search to the right if you're greater than, search to the left if you're less than. So your set is actually becoming a lot smaller. So you have this huge array that has like 20 items. If you find that you're less than the value in the middle, then you're going to search like the first 10 items. Right? If you find out you're smaller than the value in the middle of those 10 items, you're going to search the first 5 items of that, right? And it's to keep getting smaller and smaller. The way I like to think about it is like the way that we play the guessing game. If I told you I was thinking of a number between 1 and 100, right? You're going to guess 50 most of the time, right? And if I tell you, oh no, that number is too high, then you're going to guess 25. And then say, oh, you know what, that number is too small. Right, then you're going to guess somewhere between 25 and 50, like 35 or 33, right? And I'm going to tell you it's too small. Or, you're going to keep doing that until you find the number that you're looking for, or until you guess the correct number. But in this case, we don't necessarily have all the numbers in our list. It can be like just random numbers, but they're sorted. But if you don't find what you're looking for, then you don't find it. But it's the same way. Like you're just taking portions of it, half portions of everything until you find what you're looking for. So let me go ahead and type up an example. I already made a project for this, and I'm calling it binary search example. I made the method for it as well. I also wanted to show you the linear example. So we have a binary search and a linear search. Okay. Up here, what we're going to do is we're going to make a list of integers and call it numbers. And these have to be sorted. Actually, well, if you're doing a linear search, it doesn't have to be sorted. But if you're doing a binary search, it does have to be sorted. But I'm going to go ahead and sort them. I'm going to say like 3, 6, 9, 11, 15, 17, 21, 22, 22, 27, 31, 38, 43. All right, I'll stop there. And what I'm going to do is I'm going to look for a particular value. Let's just say I want to search for 7. Okay, and what I'm going to do from here is I'm going to invoke one of these methods. So the first one I'm going to invoke is the linear search. That was the easier one to do. I'm going to say int result. Result is going to be my linear search. I'm going to search numbers for a particular number. I'm going to say, okay, well, if result is equal to -1, then we're going to say system.out.println could, actually we'll just say num was not found in array. The else case would be that it was found at a particular index. So num was found at index result. All right, so I'm going to make these two methods. I haven't made them yet. That I'm going to use to do two different types of search. The first one is the linear search, and the next one is the binary search. So for both of them, what I'm going to do is I'm going to return negative if I don't find -1 if I don't find the value, and I'm going to return, or I'm going to return the index if I do find. So just to get rid of the error that was in the binary search, I just went ahead and returned a -1. I'll go and write that later. For the linear search, this is pretty straightforward. I mean, it's just a for loop. Int x is equal to 0, while x is less than the length of the array. You're going to increment x. And what we're going to do is we're going to say if the values at x, is equal to our needle that we're looking for, then you found what you're looking for. You can break, do a found or whatever, but I just think that if once you find it, you just return, like you can just stop right there. You basically leave the method. If you make it outside of here, then what you do is just return -1. That's just the way, I think the best way to do it is. Okay, but the other thing, what I want to do is maybe print out how many executions or how many statements we had to run. But we'll do that later. Like once I have my binary search written, we can compare the difference between the two. Okay, so I'm going to go and run this. And 7 was not found in the array. I'm going to put this to 31. 31 was found in the array. All right, so you're basically just going through the whole array. Now, this is the most expensive way of searching because you're just going down the line. So and you're looking at every item. So like if this array was like really huge, you have to look through every item. Okay. Now the way the binary search works, it's going to search the middle, like the way we play to guess my number between 1 and 100 or 0 and 100. You're going to search the middle, and then like if it's greater than less than, you search the other side. So you have to assume that the array is sorted before you actually begin your binary search. So in order to use a binary search, you need a few integers. You need the min value, you need the max value, you need the mid value. You also need to have, you probably get away without having a Boolean, but I'm going to have a Boolean called found. I'm going to set equal to false. I'm going to initialize min to be 0 because all arrays start at 0. And then I'm going to have a max, and max is going to be values.length minus 1 because that's my biggest index. And then I'm going to go into a loop. I'm going to make a do loop. Okay, I'm going to say while you haven't found what you're looking for and min is less than or equal to max, then what you want to do is you want to keep searching. Okay, now this is where it gets kind of funky, I think. Mid is going to be equal to our values of min plus max divided by 2, right? We're searching for what's in the middle. Now, what's interesting, the reason why I think this is kind of funky is because a lot of times you think, okay, well, if you're having everything, then you just want to know, okay, well, what's my range between min and max? The difference between the two is what's going to be the numbers I'm searching. That is correct, but then there's this offset because even though you're searching a portion of the array, you can't just use the difference between min and max. Like you'd have to use the entire set of numbers. So your min, you're basically setting your min like, okay, well, your min is always going to be 0, but if you say like, hey, I don't need anything from index 5, from index between 0 and 5, then your min will be 5. Okay, and the reason why you don't just use the offset is because you need the real actual value of the index of the entire array. I don't know if that makes sense, but maybe like when you look at the logic behind it, it might make sense, might make more sense. But once you find your mid, we're just going to check immediately, okay, well, does values at mid, is that equal to the needle that we're looking for? If it is, then we can say found is equal to true. Okay, if it's not, then what we can do is check to see if needle is less than values at mid. All right, so if you're less than, you want to, so basically what happened here is we looked at mid, we're assuming the array is sorted. So we said, you know what, I checked mid and needle is less than mid. So that means anything from min to mid is where I want to search now. So what we're going to do is we're going to set our max equal to whatever our mid is minus 1. Okay. We're adjusting our max to basically not include anything to the right of the mid index because everything to the right of mid index is greater than mid and we no longer have to search that. So we're kind of adjusting our data set size as we check what's greater than or less than. The else case would be us saying, okay, well, min is now mid plus 1. Okay, this is the case to where you looked at mid and you're greater than mid. So now you adjust your min and you say, okay, well, now the smallest index that I want to search is whatever mid is plus 1. So now you can search from wherever mid is plus 1 to whatever your max is. And really that's it. I mean, all we're doing is adjusting our min and our max and figuring out our new mid. And what we're going to do here is instead of returning -1, we want to return, if you're able to find what you're looking for, then you want to return the mid because that's where you found it. If you did not find what you're looking for, you return a -1. Okay. So instead of using the linear search, we're going to use the binary search. Now I'm going to run this and it said 31 is not found in the array. What the heck? There is 31. I must have done something wrong. All right, let me look at what I did. Oh, I did do something wrong. I put min here. That should be mid, okay, because you always want to grab the value at mid. So let me run this again. 31 was found at index 9, and that is true, right? 31 is right there. If I put in a 7, let's see what happens. All right, 7 was not found. All right, so let's go ahead and try to add different counts on this. So let's see, how do I want to do this? All right, so what I'm going to do is right before we return, I want to print out, I'm going to have this other one called count. I'm going to set it equal to 0. Okay, and every time I do the loop, I essentially want to increment count. Okay, and before I return a value, what I want to do is say system out print line, and I'll just say count. And count's going to be how many times we iterated or did the loop. So for the linear search, I want to do something similar, except count would be x, right? So we're going to return x. All right, so what I'm going to do here, let me say int x. And if I return here, what I'm going to do is say system out print line say whatever x is plus 1. And I'll print it out here as well. All right, so that we can see how long it took us to find each one. All right, so I'm going to just copy what I did here. And I'm going to call this one result 2, result 2, result 2. And I'll change this to linear search. I'll keep this one up here, binary. All right, so I have binary search, linear search. I can get results on both of them. I want to see which one took the most steps. So the binary search was able to determine 7 was not found in 4 steps, where the linear search needed 13 steps in order to determine that the 7 was not found. I'll put a new line right there. Okay, so let's see what happens when we put 31 in again. 31. All right, so the linear search took 4 steps. The binary search took 4 steps. The linear search took 10 steps, okay? So the binary search is considered to be a lot more efficient. However, there are some cases where the linear search is more efficient, like if the very first number you're looking for is the lowest value in the array. So if I were to run this, you can see binary search took 3 steps and the linear search took 1 step, okay? If I were to make this a 6, the linear search would still win. It would take 2 steps, and the binary search took 4 steps in order to find 6. All right, so there is some trade-off. However, for a large enough set and a more randomized number, the binary search is a lot quicker because it just immediately eliminates parts of the list of numbers that it doesn't need to check. Now, you do have to have the list of numbers sorted in order for the binary search to work. So if it's not sorted, then it's not going to find that number. Linear search does work both for sorted and unsorted values or list. So the linear search has the advantage there. It's just going to take a lot longer to find that number.